So, we will look at the 4 position synthesis for motion generation. Now, if you remember, in the graphical methods we stopped with 3, right, because we ended up with a unique solution. So, essentially the strategy that we used was, okay, the moving pivot will move along a circular path. So, up to 3 positions I can find the center of the circle that passes through those 3 points, and then I am, so but I ended up with a unique solution in that case. But if you look at the table that we did for, when we looked at the diet synthesis method, and you look at so if you look at a diet E power I phi 2 minus 1 gamma 2 minus 1 equal to delta 2. You have what is given are the deltas and the gammas, because this is a motion generation problem, and your unknowns are Z1, Z2, then phi 2, phi 3, phi 4. Okay. So, equal to 7 scalar unknowns. You have 6 scalar equations above, 7 scalar unknowns. Therefore, you still have one free choice, okay, which means theoretically you should have an infinity of solutions, right. But we saw with the graphical method that we ended up with a unique solution for the 3 position problem, and we did not explore the 4 position, although some clue you have, like for instance if you take the pole, okay, if you take for 2 positions, if you take the pole say P12 as one of your moving pivots. Now, what happens in position 1 and position 2, the location of that does not change. So, I can actually, if I choose that as a moving pivot, I can actually reduce the 4 position problem to a 3 position problem, because one point does not change between 2 positions. Okay. So, there are graphical methods, it is called point position reduction. Okay. There are graphical methods, but we did not go into that. Essentially you do have, we saw that you do have a free choice. The question is, how do we exercise that free choice, maybe not graphically, but how do we solve this problem. So, we should have an infinity of solutions. So, we saw that the strategy was, okay. So, if you take the 4 position problem, okay, if you take 4 positions of this thing in the plane of the coupler, and I find corresponding, say for the 3 positions I find OA and some OB. I am just drawing it randomly, but say I find the corresponding center points, right, for these 3 positions. if I take say 1, 2, 3 and then I take 2, 3, 4, the odds that OA and OB will, that A4 will also, A4 and B4 will also lie on the circle passing through OA and OB, you know, which satisfies the first 3 position, is very low. Okay. So, that is not going to happen. So, if I synthesize for 3 positions and add a third position, it is not likely that the fourth one is going to be on that same circle, right. So, the question we want to ask is, are there certain points on the coupler or the moving plane such that, you know, you can find a circle that passes through all 4 of them. So, that they will lie on the same circle. So, are there points K in the coupler plane such that its corresponding four positions lie on a circle centered in the fixed plane centered in the fixed plane for the 4 arbitrary positions of the coupler. Four arbitrarily prescribed. That is my design condition, right. I give 4 positions based on some other criteria, but can I now find, you know, can I find points on the coupler such that they would still lie on a circle centered in the fixed plane. Okay. So, that is the task that we have. So, this question was asked by Burmester. So, this theory is called Burmester theory in 1876, and he figured out the solution to this as well. So, the Burmester theory was proposed in 1876, which basically deals with the 4 position problem of motion generation. So, now let us go back to the equations. You should be able to write these equations in your sleep now. The standard form e power I phi 4 minus 1 delta 4, right. So, here the unknown angles, okay. So, the unknowns are Z1, Z2, phi 3, phi 4, and the unknown angles are in transcendental form. Okay. You do not have up to 3 positions. We saw we got a nice set of linear equations that we could solve for the diode, right. Now, that is no longer the case. Okay. We saw that even with the in the case of specifying the fixed pivot, even for the 3 position problem, if you specify the fixed pivot, then you actually get, you have to satisfy a condition, a compatibility condition, so that which is transcendental in form, okay. And we did that with the using geometry, right, forming that triangle. We had that d1 plus d2 e to the power phi 2 plus d3 e to the power phi 3. Okay. So, you have already seen that kind of a form. This is sort of an extension of that. So, you will see here that these angles are in transcendental form, and therefore, these equations are not easily solvable. Also, you have only you want to really solve for z1 and z2, those are what and you have only one free choice, but no matter what I pick as my free choice, the other angles are still unknown. Okay. So, the three unknown therefore, you need some kind of a non-linear technique. So, I can write this in matrix form. I can write this set of equations as okay, the same equations can be written in this form. Okay, same thing. So, this is if I want this system to have a solution for z1 and z2, okay, then the determinant of my augmented matrix has to be 0. So, that is an additional condition that I have to satisfy, right. So, that means two of these equations should be linearly dependent, right. I can have only two sets of linearly independent equations out of the 3. So, the coefficients must satisfy certain what we call compatibility conditions. So, the compatibility condition for this becomes basically you are saying the rank must be 2, right. So, the determinant of the augmented matrix should be 2. So, I can first write this as no, I won't write that. Okay. So, the solution to that exists only if this determinant minus 1 e power I gamma 4 minus 1 delta 4 equal to 0. So, this is the determinant of that matrix. So, I have only one free choice. Okay. Let us say I take, let my free choice be phi 2. So, in this the second column everything is known because gamma 2, gamma 3, gamma 4 are specified. Again third column delta 2, delta 3, delta 4 are specified. So, let my free choice be phi 2. So, I will expand about the first column. Okay. So, I can say delta gamma 3 minus 1 minus delta 3. Remember delta, all these are complex numbers, the deltas, and so are the e to the power I gamma 2, gamma 3 etc. Okay. Minus, I will expand about the first column because that is where the unknowns are. Plus e to the power gamma 2 if I expand these and simplify, I get, I will use delta 2 e power I phi 2 plus delta 3 e power I phi 3 plus delta 4 e power I phi 4 plus delta 1 equal to 0, where delta 1 is based on the first position minus delta 2 minus delta 3 minus delta 4. This is what I get if I expand this. Okay. I get this in this form. What does this form remind you of? Remember, these are all complex numbers. Does that look familiar? This looks like the loop closure equation for a 4 bar with fixed length delta 1 and the other 3 links delta 2, delta 3, delta 4. Okay. So, if I take phi 2 as my free choice, that becomes the input to this 4 bar. Do you see that? So, this is, so in the first position it is delta 1 plus delta 2 plus delta 3 plus delta 4 equal to 0. That is my loop closure equation. Then I give everything a rotation. Delta 2 I rotate by phi 2, delta 3 then rotates by phi 3 and delta 4 rotates by phi 4, and still the loop is closed, which is just like your 4 bar. This is a different 4 bar. This is a 4 bar. We are not talking about the 4 bar that we are trying to synthesize. Okay. So, this is basically the compatibility condition can be thought of as a 4 bar satisfying this loop closure equation, where the lengths are basically delta 1, delta 2, delta 3 and delta 4, and all these deltas are based on known quantities. So, let us write that. So, delta 2 is, these are basically the cofactors. Sorry. Delta 4, delta 3 equals and delta 3, sorry, delta 4 and delta 1 equal to minus delta 2 minus delta 3 minus delta 4. All the deltas are known. Why? Because they contain only input data. All the gammas and deltas are known. So, all 4 deltas are known. So, this condition, this delta 1 plus delta 2 e power I phi 2 plus delta 3 e power I phi 3 plus delta 4 e power I phi 4 equal to 0 is the compatibility condition. What that says is, I can choose this phi 2, phi 3, phi 4 have to satisfy this condition. I can choose my phi 2 and then my phi 3 and phi 4 get determined by this condition. So, I cannot use any random group of phi 2, phi 3, phi 4 for my solutions, right. For a particular phi 2, phi 3 and phi 4 should satisfy this condition in order for me to have a solution for Z1 and Z2. That is what this essentially tells me. Okay. So, this resembles a loop closure equation for a 4 bar formed by delta 1, delta 2, I can mod of, if I take those as the link lengths, right. So, in the first position I have delta 1 plus some delta 2 plus delta 3 delta 4, that is equal to 0. Okay. Now, I rotate, if this vector I rotate by some amount, okay, then this vector becomes, delta 1 remains the same, it is the fixed link of this 4 bar. You see there is no phi 1, there is no angle associated with that, it depends on, I can think of that as a constant, and then this can be thought of as, okay. So, this would be delta 3 e power I phi 3, this would be delta 2 e power I phi 2 and this would be delta 4 e power I phi 4, where the angle is from the origin. Okay. So, I can think of it in the this way. So, I can use this. So, it is essentially solving for the other two angles in the 4 bar. Okay. By now, if you do not have that code, you probably want to create that code for, this is the position analysis code for a 4 bar, to find those angles and to draw the 4 bar in that position. Okay. So, because that is the reason you are going to use it again and again, this code, okay, for this. You can also look at this as, because phi 2 is your input, your free choice, I can also use the same code that I wrote for my other one, that D1 plus D2 plus D3 for the fixed pivot, because this vector I can take it and I can call it repeatedly. I can check compatibility by doing that, because this then becomes a known quantity, right. So, I can look at this as delta 1 dash equal to delta 1 plus delta 2 e power I phi 2. So, I can say delta 1 dash plus delta 2 e power I phi 3 plus delta 3 plus delta 4 e power I phi 4 equal to 0, which is what I used for the previous, for my where I specified the fixed pivot. Remember, I had to solve a transcendental equation there. So, you can repeatedly call that for each phi 2. That is another way you could do that, but I think it is useful to have this 4 bar position analysis code. It is useful for you to do that. And the circ command makes it really easy to write. So, you solve this compatibility condition, and then so for each phi 2 I will get what? I will get a phi 3, phi 4 and a phi 3 dash, phi 4 dash. Why? Because of my 2 assembly modes for the linkage. Okay. Because of the 2 assembly modes for the linkage, I will get these sets. Okay. So, if assembly mode 1, if it is phi 3, phi 4, assembly mode 2, I will get phi 3 dash, phi 4 dash. Okay. So, then once I get this, I can use 2 of these equations, 2 out of the 3 equations, because now I will have the specific phi 2, phi 3 combinations that will work, that will satisfy the compatibility condition. So, I can take any 2 of these equations, plug in the phi 2, phi 3, or depending on which equations I choose, and find the Z1 and Z2. Then it becomes just a linear system. See, earlier we were able to, like for the 2 position problem, right, we were able to pick phi 2 and phi 3 as free choices and solve for Z1 and Z2. Sorry, for the 3 position problem. Okay. For the 3 position problem, we picked phi 2 and phi 3 as free choices, made this a linear system of equations in Z1 and Z2. Now, I can't choose arbitrary phi 2 and phi 3. I can choose phi 2 and phi 3 such that it satisfies that compatibility condition, okay, which means essentially solving for that 4 bar. So, specific values, specific combinations will give me solutions for this. Phi 2, how many choices do I have? I have an infinity of choices. So, again I can technically solve the 4 position problem. I do have an infinity of choices. So, I should have an infinity of solutions. So, I will just show you. So, if this is my coordinate system, I have this point P. I have solved for Z1 and Z2. I can basically find, so I will call this point circle point in the first position. So, I will call it K1. This is the fixed point. Remember, M for middle punct. So, it is the middle center point. Okay. So, and K is the circle point. So, I can, so this vector M will define that and K1. Okay. So, I can my circle point, this is R1, right, which is known. my first position, my first precision point. This should be P1. So, circle point K1 is defined as R1 minus Z2. Okay. R1 minus Z2 is K1, and then my center point, moving pivot, or my center point or fixed pivot, M is K1 minus Z1. All these are vectors, so I will just okay. So, this set this combination of K and M, it is called a Burmester point pair. Okay. So, BPP, Burmester point pair. Because it says that for a specific circle. So, if I find the locus of all the points K1, okay. So, see, I have found out Z1 and Z2, I have solved it for different values of phi 2. Okay. I have taken phi 2 as my free choice, I have solved the compatibility condition. So, I have sets phi 2, phi 3, phi 4. I have several sets of those. Using that, for each set I can find a Z1 and Z2, correct. So, from that if I find, so now I have the locus, if I plot all those points, okay, I get a locus of all the possible circle points, okay, for which I can hit these 4 positions. And for each of those circle points, there is a specific center point which is determined by this relationship. So, I can choose my circle point, I can, so once I draw the curve of all possible circle points, once I choose a circle point, which means I specify my K1, then M becomes completely determined, because M equals K1 minus Z1. I have solved for Z1 and Z2. Okay. So, for each circle point there is a corresponding center point, or for other way around also. I can choose, so I can choose my fixed pivot instead. I can choose my center point in the fixed plane, in which case I will know exactly where my circle point is going to be once I plot the locus of these points. So, I will just show you. So, a plot of the, okay, let me just write this down and then, okay. So, you get 2 sets of the Burmester point pairs. Why 2 sets? Because again phi 3, phi 4, phi 3 dash, phi 4 dash. So, for 2 sets, one for phi 3, phi 4, one for phi 3 dash and phi 4 dash, with phi 2 being varied. So, for each phi 2 you will get 2 sets of Burmester point pairs. So, a plot of the center points for each value of phi 2 will give you 2 branches of the center point curve, one for the compatibility equation in mode 1, the other for the compatibility equation in mode 2. Center point curve is called the M curve. because one branch is associated with phi 3 phi 4, another with phi 3 dash phi 4 dash. So, if the compatibility linkage, if that allows complete rotation of the delta 2, then the two branches will meet, okay, and I will show you that. Do not confuse the compatibility linkage with the linkage that you are trying to design. Okay. So, and similarly you can plot the circle points can also be plotted to give the circle point curve, K curve. Okay. So, every point on the center curve or the M curve is a potential fixed pivot, right. Every point on the M curve is a potential fixed pivot. Therefore, now you have an infinity of solutions as long as it lies on that curve. You pick a point on that curve, there are an infinity of points on a curve. So, any point that you pick is a potential solution for the fixed pivot. Once you do that, the corresponding circle point gets fixed. So, you cannot pick any point on the center curve and any point on the circle point curve. You can choose one or the other, because only then your compatibility condition will be solved. Okay. So, then you can form dyad for one side. Similarly, choose another center point on the curve, find the corresponding circle point, you have a second dyad, you can form your 4 bar. Okay. So, let me just show you. So, you can write the code for this, but this is, I have 4 positions, okay, 1, 2, 3, 4, and therefore, the corresponding rotations delta 2, delta 3, sorry, gamma 2, gamma 3 and gamma 4. This one with the circles is my K curve, that is my circle point curve, that is why I put circles so I would not forget. The other one with the stars is the locus of my fixed pivots. This is only for one mode of the compatibility linkage. Okay. Let me see if I have the other one. This is for the other mode. So, this is the second M curve, second K curve. This is the first M curve and first K curve. So, this corresponds to phi 3 phi 4, the M curve and K curve. This is for so this is for phi 3 phi 4 in the compatibility equation. This is for phi 3 dash phi 4 dash, same phi 2, phi 3 dash phi 4 dash in the compatibility equation. And if you look at it, if I plot both on the same, you can see that they meet, because this particular linkage is capable of full rotation. Okay. Now, to create my linkage, I can't do it just with the what I have here, because I do not know which point corresponds to what, but essentially I could pick one of these as the fixed pivot, but I will have to look to see which one of these circle points corresponds to that fixed pivot. So, I can choose anything on this, the one with the stars, right, that gives me all the choices for the fixed pivot. Okay. So, for one diode I can choose a fixed pivot on this, does not matter, I can choose anything on this, find the corresponding circle point, okay, and then if I connect it to the first position, that gives me my first diode, right. So, I think I have, so here I pick this as my one fixed pivot, I found this is the corresponding circle point, this is my first position. So, these squares are P1, P2, P3 and P4 corresponding to R1, R2, R3, R4. Okay. So, these are the precision points P1, P2, P3, P4. Okay. So, I can pick one diode, then that becomes my, so this becomes my Z1, this becomes my Z2. Remember, your diodes go from the fixed pivot to the coupler point. So, what is my coupler here? This link is my coupler link. So, the other diode that I have chosen is this one. Okay. So, I have chosen another fixed pivot here, its corresponding circle point is here. Okay. So, this becomes my second diode. So, this could be Z3, Z4, and so this becomes my linkage. This is the, so this triangle will be the coupler link. Okay. Maybe I should make this also blue. Just do that. This, and this. Okay. So, this is how I get an infinity of solutions. Yes. No. So, you can choose, so here, so I can choose my diodes anywhere. I can choose one diode from, because it is only the corresponding circle and center point that matters. So, okay. Yeah, for the 4 bar. For one diode you have an infinity of solutions, therefore, you have infinity square for the 4 bar. Okay. So, this is the coding takes a while. So, it goes by in a flash in class, but so anyway you can do that. Okay. So, that is your 4 position. So, this can give you a clue. So, if I want to do 5 position synthesis, okay, I essentially have no free choices, but this should give you a clue. So, if I take positions 1, so I have 5 positions 1, 2, 3, 4, 5, and if I look at, I take them 4 at a time, say 1, 2, 3, 4 or 1, 3, 4, 5, okay, and I plot these, and if I can find an intersection of the M and K curves, then that is a potential solution. Okay. There is lot of mathematics and this thing. I have just plotted some. So, no, this is just both of this is for some other set of conditions. So, they can look very different. So, the first one was for certain, this is set 1 and this is just for a different precession points and rotations of the coupler plane. So, you can see here in this one they do not meet, okay, which means the compatibility linkage does not close for certain positions. So, gamma that delta 2 may not make a full rotation. In the compatibility linkage you can't close it for all values of phi 2. Okay, so, there is a gap. In the previous case where it was able to make a full rotation, those two curves met. They in this case that is not and again this is another set of diodes. So, here so you can get some funky looking that will be this thing and this will be the coupler plane. This triangle is the coupler plane. So, 5 position synthesis essentially you can take, do I have the other one? So, I can take the 1, 2, 3, 4, 1, 2, 3. So, I can try to find intersections and see if I can. So, you can get a maximum of 4 Burmester point pairs. So, 4 real solutions for diodes. So, those diodes can be put together in 4C2. So, 6 linkages you can get by up to 4 Burmester point pairs, because when you solve for the betas you will get like a quartic equation and you can have 4 real roots maximum. So, you will have 0, 2 or 4 solutions for the 5 position problem. Okay. So, you can get 4 Burmester point pairs for this, for solving this 5 position synthesis. Okay.